Hi, this is Neil Bulger of A2 Efficiency, and I'm going to be talking today a bit about designing for resiliency and passive survivability. This is a presentation that we have shared a few times and updated a few times about ways to design for building envelopes which can withstand heat waves, mild or hot climates, uh, and really building on some great work that has been done elsewhere in the world around this topic. So most recently, we presented as part of the Inland Regional Inland Regional Energy Network, the I-REN group, which did a great presentation on this topic in October. And so we wanted to share that same presentation with everyone else and provide some insightful information. So a lot of this work kind of builds on the shoulders of lots of other great standards. I like to think of the work we do around advancing building capabilities, starting with energy efficiency, right? In California, we've developed these great building codes which have really driven energy efficiency in all building types in a lot of ways, both around the envelope, towards heat pumps, electrification. There's now a lot of focus and great ideas building on the energy code that are coming out of the passive house principles, thinking about the envelope, thinking about air quality, air tightness, how we can balance ventilation, a lot of just like best practices, I'll say. And then that really does, in my mind, dovetail into resiliency and how we think about buildings as resiliency hubs. This is just an image here from Dave Baker Architects about their thoughts around how we think about buildings as resilient hubs and what that means. And so, between these is kind of where the work we're going to talk about today sits. So I'm going to just talk about a piece of resiliency around heat stress. And what we think of when we say the word passive survivability is a building's ability to maintain critical life support conditions in the event of an extended loss of power or water or a heat spill, right? In this case, an extreme weather event. And in California, we actually have a lot of buildings that have air conditioning, but I think an insightful study came out of UCLA in 2022 that really talked about access and affordability. And while there might be that approximately 20% of owner-occupied units and 29% of rentals in California don't come with air conditioning. By code, they have to have heat. You have to be able to heat a building, but you don't necessarily have to do cooling. And in a lot of California coastal climates, that's fine most of the time. A lot of regions, it's fine all year round. Though, as the climate does change, we are starting to get these peak events. And so we might start by thinking, well, 20 to 29%, that's a small amount. Though then, more importantly, we start to think about how there's a majority of these houses, the older houses, which actually have poor envelopes, really do often lack, even if they had cooling, lack the envelope, which could ride through some of these heat waves. Oh yeah, but the other part I wanted to mention is that even though we might have cooling in these homes, there's an affordability aspect, right? Do we run the cooling in these critical times when energy rates are quite high? Maybe people are not using them as often as they might need to be. So when we start to think about architecture and great building designs and ways we could design for passive survivability, I picked up this quote from Corey Squires of Bora Architects, who talks about how the most effective strategies have been around for as long as buildings have, and how there's nothing new about these design concepts. It's the same concepts that have built passive designs, well-shaded mass, highly insulative walls. All these strategies have existed for millennia. We just have to think about how to apply them. So as we think about a building envelope, right, we have this thermos that we're dealing with. And so we're trying to maintain a environment inside that can be comfortable and really just survivable, right? So we have to consider what are the solar heat gains, what is the insulation of the envelope, what's the orientation, how is this going to affect the people inside the building. And I'm inspired by work that some of my colleagues have done, just thinking about comfort in the environment and spaces in between buildings. And I start here because it's a really powerful metaphor, and I really a powerful relationship to think about comfort, and some examples of how we can think about our relationship to the built environment. So if we look at Abu Dhabi, where it's consistently 100 degrees or hotter outside, and work that was done there when they built Masdar City, they started by looking at if the outside air temperature was above 100, in this instance 126, the ground that's absorbing all the sun's irradiation is much warmer, right? It's almost 10 degrees warmer, 135. And so could we design an environment where we protect the ground, right? Even when the air reaches 99, the ground has been shaded throughout the day before, and now we have a ground surface that's only 91 degrees, where a lot of people are walking and can feel more comfortable. And I then just Googled images of buildings in and around that city, and a great takeaway I had is every building had shading, right? This is a very hot climate. You can see these extensive shades on this 4-story building. Here we can just see an example of self-shading on the facade, even just using this ability of the overhangs and the patios to provide shading to the stories below. I thought a very creative strategy for providing shading within the architecture of the building. And then a fully shaded outdoor area, right? So this is, again, that area we were looking at before, where between buildings, they've done a lot to understand where's the sun going to be, how can we ensure the ground level stays as cool as possible. And you see some of these great examples even locally in the Bay Area in California. This is a building by LMS Architects, where we can see kind of a lot of these same strategies at play, simple shade elements that are built into the window wall package, the ability to orient parts of the facade to provide shading, right? Changing the orientation of this window, shading the top part of it, also providing shading below. And knowing that these shade scrims are even possible add-ons to those window wall packages. They don't have to be extensive for them to provide an effective level of shading to a building. Another project by LMS, I just thought another elegant solution of, again, kind of a shade that wraps that window box. And again, the ability to use the facade to provide that level of self-shading and setbacks. Another strategy we have started to think about more is expanding on what is the Cool Roof Council. The Cool Roof Council was started back as part of the 2005 Energy Code in California to set requirements for solar reflectivity of roofs. Well, they also have cool walls. They have a database of products that rates the reflective materials of wall products, paints, and it's not required now, but it certainly serves as a resource to understand what one material might be able to provide compared with another one. So when we think about overheating in buildings, we're actually going to do an experiment where we pulled from work that was done in the UK as part of the Chartered Institute of Building Services Engineers, CIBSE. And way back in 2013, they developed a guideline for limiting thermal comfort to avoid overheating in buildings. This was coming out of a lot of heat waves that were there, and it evolved from understanding at what point in indoor temperature does it become impactful and critical to maintain human health and life. And how might we design buildings to do an assessment when they're designed, new buildings in particular, to avoid critical overheating problems that might occur. And this standard evolved. They ended up making design guides. It really focused on mid-rise and high-rise residential type applications. Those certainly could apply to any building where people are going to be. And now it's even a part of their codes. They now have energy codes, ventilation codes, and they have another part O, an overheating standard, where you have to do this assessment for certain building types. So we thought it would be fun to go through that overheating assessment in a California building and see if we applied those same requirements how would a building perform, and how might we be able to improve the envelope to change its performance. And the criteria that guideline sets, there's 4 criteria. We're going to look at the primary ones that have been around forever, the top 3. So those are 3 limits on how the indoor condition can maintain a level of survivability. The first one's an annual limit. The building can never exceed the outdoor air temperature by more than 3% of the time. The second one has to do with a maximum duration during a critical day. So you can imagine on a certain day, in a consistent 6-hour period, we don't want the indoor environment to ever exceed the outdoor by a total of 10.8 degrees. I converted this all from Celsius, that's why we have decimals here. But right, you could think of it basically as like, we don't want to have 6 hours of persistently warmer than outside. That can be bad for human health, especially the elderly or young kids. And then the last one is about a peak number, right? So at any given instant, we never want the indoor condition to exceed the outdoor, even for an hour, by more than 7.2 degrees. And so these checks can essentially be done, and the standard goes on to then describe how to apply these to different building types to evaluate the performance. So we looked at a typical mid-rise multifamily housing project, or low-rise, I should say, a 2-story multifamily 16-unit building. So you can see here it has about 30% window-to-wall ratio, southeast facing orientation. For purposes of the evaluation, we ran it with operable windows, and with and without shading. We assumed natural ventilation for ventilation in the building. And the model is run without heating. We're really going to study the hotter climate, hotter months of the year, but we will look annually at the results. So just to give you a sense of the climate, we're going to look at Riverside, but I want to demonstrate here the challenges that face us with looking at weather and peak weather events, right? So this is the typical weather range for Riverside, Palm Springs, and San Bernardino. You can see in Riverside, San Bernardino, both in the high 90s in July and August. Palm Springs getting up warmer up to 106. But what we're looking at is really like the typical for each location. The typical temperature in August on a high day is 94. But when we actually start to look at an actual weather event, you can see here in August, September, that same location hit 115 in September, 107 in August. And you can see it here where the typical is represented in this red area. And then the actual measurements for that year are shown in gray. So we're close, but we get these events, these high events, and we need to be able to design for those high events and understand how people are going to survive them. Same in San Bernardino, almost identical, a little different, right? 115, where the average is closer to 100. So we looked at this building, we thought, okay, we have the newest building energy code that's going to come into effect January 1st, 2026. We could start there to understand how would the building have to be built. This is a new building. What does our glass need to look like? Our wall insulation, roof insulation, air leakage, and what level of shading is required, right? So in the code, technically no shading is required. And then we looked backwards. We said, well, what would a building be made up of if it had been built in 2005? Or in this case, I guess it'd be in like 2007, when the 2005 code was required. And so this might be a modern existing building, right? It has a level of glass that's a solar heat gain of 0.4. Some roof insulation, right, R16, some wall insulation, R8. About the same infiltration. There's been a lot of studies on air leakage in California buildings. A lot of them tend to be about the same. You could certainly tighten it. And then we looked at the other side. Where could we go further? What do we think are solutions people could do today within their realm of reach that maybe cause some additional thought and design architecture to consider, or space requirements for insulation, but nothing far beyond what we've seen, right? More insulation in the walls, R20 walls. Maybe that requires another inch of continuous insulation. A thicker roof, R50 in the roof. And then even picking materials with higher reflectance, right? This again, we could talk about how the wall reflectance might be at 0.3 in this design here, just based on a general wall. We could raise the reflectance using the database from the Cool Roof Rating Council and adjust that. We lowered infiltration, right? There's a lot of thought now around air leakage and air testing in buildings, so trying to make a tighter envelope. And then adding shading, right? Fixed overhangs. For purposes of this example, we just added a quick overhang, 2 overhangs on every south, east, and west facade in the building. And so what we see, I just zoomed in here on one day in June. So this is the 30th of June in Riverside, and we're looking at results of the 3 buildings. So this is a day where the outside air hits 102 degrees. And we can see inside the existing building hits 94 degrees, and we can basically see the heat build up in the space, right? The air outside is hot, the sun is high at 1 o'clock, and we're building heat into the mass. And then that sort of rides almost till 10 o'clock when the air temperature finally drops and we're able to exhaust some of that heat, open the windows back up. And as we look towards what we could achieve in a new building built to code today, we could bring that indoor temperature down 4 degrees, 90 degrees. And then looking beyond that, bringing it down another degree through this high performance envelope changes. So this is just one day, but now we're going to walk through how this rolls out in a whole year, but I just wanted to demonstrate how this looks. And this is all applied to this one apartment down here we're evaluating on this southwest corner. So if we look across all the apartments, right, I said there's 14 apartments, and there was those 3 tests, the annual test, the daily test, and then the critical peak hour test. In our existing building, only 4 of the units passed. The 4 units that passed are probably on the northeast side of the building, a little protected from that afternoon sun, but 12 of the units failed in some criteria or another. As we move into the newest building code, we do a lot better, right? 11 of the apartments passed the criteria, but 5 failed. And then as we do these enhanced envelope performance measures, we move towards 14 of the 16 apartments past the criteria, 2 still not quite making it. And to understand this a little bit more, I just zoomed in again on another day. I think this is actually the same day we were looking at before, to understand like that persistent story. So we can see here I've highlighted like how many hours are at 90 degrees or above inside the building. And I know the whole standard is around relative to the outside, but just to give a sense in a number for people to understand, right? We're going from a 10-hour duration inside above 90 in this apartment to 7 hours down to only 4 hours above 90. So a pretty good decrease in the amount of durations of indoor extremes. And as we look at those criteria that we talked about for overheating, where did the projects fail? So they mostly struggled in the annual and the daily limits. The high performance one more passed, but still there was a few apartments that exceeded 3% and on a certain day exceeded more than 10.8 total degrees throughout a day. There's certainly ways they did improve, I will say, vastly from the 5 that failed here. The 2 that failed here were on the edge of failing. Still, it does beg the question, well, what strategies would work? Would we need more mass? Is there even a diurnal swing great enough in Riverside that could provide a level of cooling the day before a heat wave? Or is it not possible, right? Or do we need to plan for some level of cooling, even a small amount, that could provide just critical life support, right? If we had a backup power system, a small backup AC, how much conditioning do we need? And that similar approach is how we've actually designed other multifamily buildings, really from a comfort and a cost and a constructability perspective. So this is from a project where we did this exact same thought exercise, and it was really driven from a cost and affordability perspective, where we said, if we were to pick the smallest wall-mounted system we could buy and put on each wall, how big is it? How much cooling can it provide? And if that was our threshold, what does the envelope need to look like to get to that level of heating and cooling? Do we need more insulation? Do we need better thermal bridging strategies? Do we need better shading on the south? Do we need a ventilation heat recovery device to reduce our heating after we've managed cooling? Because ultimately we want to buy the smallest system possible. And so that same strategy is becoming more and more common, and manufacturing is really rising to the challenge. And I just wanted to share now some of these product innovations, I think, that are really coming to the multifamily environment for either all-in-one units or just these very small heat pumps that can do that small amount of cooling and heating. So this is a small single unit providing ventilation, and it uses that same airstream to provide a level of cooling and heating. And so it's not a lot, right? It's 1 to 1.3 tons, but it's in one room providing that apartment a level of cooling. This is another unit that is more like a cabinet in the wall. But again, the whole point of this unit is has almost the same capacities, but it's a vertically integrated system. The goal of this product is to really figure out, well, how do we integrate for all the functionalities the house needs? Maybe we have kitchen exhaust, and maybe we need to then reduce the amount of penetrations in the facade. I need air coming in, air going out down here. But again, trying to minimize those punctuations to the outside and then make it as small as possible to really maximize the livable space in these apartments. So those are just some examples of innovative strategies and ideas, again, to provide a level of heating and cooling and really bring loads down. Thank you all so much for time. And if you ever have any questions about the SIPC standard, about the analysis we did, we're happy to share. We really think this framework and guideline part O, even though it's in the UK and other places, has a lot of bearings that could hold in California. And while it provides a level of complexity to buildings to demonstrate they are able to achieve it, it's been proven to work for several code cycles in the UK and really has educated the construction environment to think in that capacity. What are we going to do to exceed our Part O requirements in addition to our energy and ventilation requirements? Thank you again for your time, and this is A2 Efficiency.